Okay, guys, as you see, we will start another chapter, another process, another additive manufacturing process called sheet lamination processes. We will have some examples of these, and I would like to actually start with a nice example. This is called as Impossible Object. The company is called Impossible Object. This is a primitive version of them, but now they have much powerful systems. I will first show you the primitive version. Let me arrange this one and also open the other website so we can spend some time with the impossible objects. So let me show you the Safari. Yes. This is, as I mentioned, the first prototype of the printer. You will see that they're following a totally different scheme to have actually different products based on additive manufacturing methods.
This just unveiled machine from a company called Impossible Objects is one of a number of new manufacturing processes that could transform not just how America makes things, but also what America makes. The machine is a kind of 3D printer, only it makes objects out of carbon fiber or other composite.
So they are using such kind of sheets made of carbon fiber, or even these days they can use glass sheets. They start with these.
This is a prototype, but the eventual goal is 3D printed objects that are as strong and light as aluminum, yet as cheap and quick to produce as those made out of plastic.
So they have kind of sheets of carbon fibers.
Carbon fiber has long been used to build everything from airplanes to race cars, but it is expensive and difficult to work with. The hope is that by creating 3D printers that can produce virtually any object with carbon fiber, we'll find new applications as well as.
So this is a kind of hat, and they are jetting some, depositing some agents, some special agents. We will see that the deposited regions will be actually the regions we are looking for. They will not be removed later on. They will be the cross sections we want to have in our slices.
Make its way into existing products. For example, right now only high-end consumer vehicles like the all-electric BMW i3 are made from carbon fiber. Unlike traditional 3D printers, Impossible Objects machine works by printing each layer of plastic on a separate sheet of carbon fiber or another fabric, such as Kevlar, polyester, or silk.
You see they have deposited some kind of agents here, the white regions, and they will consist of the part actually we are looking for. And these are slices, so they need to put these slices on top of each other and then do some compression.
The layers are stacked one atop the other and baked in an oven to fuse them together.
This is compressed, and they will have also done some baking in an oven. And now, finally, they will remove this
afterward. Excess material is
undeposited regions.
The result is strong, lightweight parts that can take on forms that are simply impossible to build with traditional manufacturing techniques. In addition, Impossible Objects founder Robert Swartz says that
Okay, now let's have a look at their website. They have modified a little bit. This is now their current system. The previous one was a kind of a prototype, but now they have a much powerful one, and they are working with some bigger companies. And here's the newest version.
Imagine producing complex carbon fiber and other composite parts at production speeds and volumes. Impossible Objects' groundbreaking patented composite-based additive manufacturing technology, CBAM, produces strong, lightweight 3D composite parts that are printed up to 10 times faster and available in a wider selection of materials than conventional 3D printing. Here's how it works. The process starts with a CAD model of the part. The model is sliced into thin layers and prepared for printing. The machine starts with a stack of sheets. The images of the layers are printed with an aqueous fluid onto fiber sheets. The sheets pass through a powdering system where polymer powder is flooded onto the sheet. powder sticks to the sheet where the fluid is deposited. The excess powder is vacuumed off and the polymer is selectively deposited on the sheet. Microscopically, you can see polymer particles penetrating the sheet. The process is repeated for all of the layers of the part. The sheets are then stacked to complete the entire printed geometry. The final stack is compressed and heated to the melting point of the polymer.
So it's heated to the melting point of the polymer, which is actually used to join these sheets together.
The particles melt and encase the fibers to fuse the layers together into a solid part. The fused fill block moves into the sandblasting unit. The uncoated fibers are removed, revealing the finished part. Impossible Objects C-band printing process produces stronger parts faster than traditional 3D printing methods with a broader range of material options. For more information, please contact Impossible Objects today.
These are example parts, as you see, some complicated ones. They can use carbon fibers or fiberglass sheets, but the fundamentals are the same. And do they have some information about the materials? Yes, these are the fundamentals. So you see they have different combinations of sheet metal and thermoplastic matrix material. With carbon, they can use PEEK or nylon, and with glass, again, the same. And depending on their, let's say, arrangement, they have different properties. And in different industries, you can use their, let's have a look at some industrial applications. But they're not giving much information. Any questions, guys, regarding this printer, this specific technology? No questions? Okay. Let's switch back to our lecture notes. These are the steps of this technology. They have the sheets of these carbon fiber or glass, and then they deposit some specific type of polymers on it, then remove this polymer by doing some heating, depending. This was the initial technology, but right now they have modified it a little bit. They do it with the fifth step. And you put all these sheet, let's say, parts on top of each other, press them in a kind of an oven, and then later in the last step, you need to remove these unbounded portions so that you will be just left with the desired part. And it's a nice example of sheet lamination processes. This is not available in our textbook, but a nice process. Probably in the future versions of it, they will, I think, include this one also in this chapter. Now let's discuss some history behind this technology. It's one of the, again, first commercialized additive manufacturing systems. Not actually the impossible object, but we will see that it's a bit different. The laminated object manufacturing is also called as laminated object manufacturing, or LOM. And it's very simple. In this one, you simply put layers of sheets of paper on top of each other. You may use a carbon dioxide laser to cut the papers, or you may also use some mechanical knife kind of things. But another important issue about this type of system is that the remaining part on the slice is actually divided into some squares, but in 3D, obviously, they can be named as cubes. And with the help of it, we can assume that the part is somehow printed in a kind of a bed of, let's say, paper. This is the main schematic of the process. We have a material supply here. Raw material is supplied from right-hand side and is passed, as you see on the table. We are heating with a kind of a special roller so that underneath this actually paper, we have some adhesives. And once you heat it, then it will be easily sticking to the previous layer. This is the main function of the heated roller is to join the sheet papers together with the help of the adhesives on the back side of the papers. That's why it's called as polymer coated papers. And then again, as in the case of SLA or SLS system, we have a kind of a laser, but this time it doesn't have to be a laser. It may again kind of be a simple knife, and the function of this laser or the knife is that it will be passing through the contour we have in our slice. So that this is the top view of the slice. I think we have such an contour. So our laser is moving over this contour, and the remaining regions are simply divided into some grids. So right now they are square, but in 3D, they will be actually resulting in cubes, so that after the printing is over, they can simply be taken out of these regions, and you'll only left with the part itself. So this is it, and obviously our build platform will be going downwards after each layer, and this is the kind of bed we can say, or it's called as part block, and we have the part inside of this block, and the rest is composed of simply these cubes, and they are kind of support structures. And if you are using a roll of material here, then you need to have another roll at the other side, so that excess material will be stored here. It's obviously rotating in this direction. And that is the actually basic schematic of laminated object manufacturing process. Instead of paper, you can also have sheet metal, but that will be quite difficult since cutting of sheet metal is not easy as it is in the sheet paper. Any questions, guys, about this fundamental schematic of laminated object manufacturing?
Hocam 2 sayfa önceki pipeline'da polymer deposition yazıyordu da burada nerede yapılıyor?
This is a different process. In actually impossible objects, they are depositing polymer. In laminated object manufacturing, we have polymers actually coated on the back side of this paper. So it's quite sticky. The back side of the paper is sticky. So once you heat a little bit with the help of this roller and press it on the other, let's say, layers, they will stick together. So there are different processes. The CBM, in CBM, you have polymer deposition, but in loam, they are already coated on the back side of the papers. Other questions, guys? Okay, now let's discuss some details about sheet lamination process. So we have two fundamental approaches. The first one is cut and stack, and the second one is stack and cut, which means that in the first one, you are cutting the layer first and then stacking them together. So which process is that? CBAM or loam? So we discussed up to now CBAM. This was from impossible objects, and the other one is we discussed in the previous slide, laminated object manufacturing. So which one is cut and stack, and the other one is stack and cut?
LOM is cut and stack, and CBM is stack and cut.
No. Then the answer is actually revealed. In CBM, if you remember, they had the sheets of carbon fiber, right? They were doing some operations on it, and then they were stacking them together. But forget about the post-processing. Just consider until the stacking operation. We can say that this is cut and stack, but obviously laminated object manufacturing is we are stacking on top of each other these papers first, and then doing the cutting operation. So if you look at the schematic of loam process, we are doing the stacking on top of each other. These sheet metals are stacked on top of each other, and then cut into proper shapes. So that's why it is stack and cut. And then we'll have some differentiations in terms of bonding. Some processes might be using simple gluing or adhesive. Some might be using thermal energy to bond these layers or sheets together. In some cases, we will have special clamps, mechanical clamping. To the end of the chapter, we'll discuss a specific case of it, specific case of bonding operation, in which they are using ultrasonic welding operation. These sheet metals are joined with the help of ultrasonic operations. It's quite new, and there's just a single company working on ultrasonic welding operation. Now let's briefly look at the first case, gluing or adhesive bonding. It's not a complicated, a very popular solution. We make use of papers usually, since with metals you cannot have glue underneath and simply join them by adhesive bonding. It's only possible with paper. And on the back side of paper, we have such special coating, and we can make use of laser to cut this sheet paper, or mechanical cutters can also be used. And mostly we perform bond and then form operation. So we are bonding the layers to each other and then doing forming and cutting operation. But there are also some cases where we form the sheets first and then bond them together. Now we will be first focusing on bond then form processes, which means that you will have sheet metals, undeformed sheet metals on top of each other and then do the cutting or forming operation. So we are placing the laminates on top of each other. We are assuming that if it's the first, let's say, layer, then it should be bonded to the substrate, obviously. And then the other steps are simpler. You're going to cut it with the help of your cutter or laser. And we make use of adhesive-backed rows of sheet metal. And in the schematic, we have seen that sometimes there are heated rollers. With the help of them, the plastic coating is melted, and it helps actually for the bonding process. Another issue about the forming is that your laser or the mechanical cutter just be cutting one layer thickness. If it's cutting more than that, then you will not be able to obtain the proper 3D shapes. This is an important issue for bond and then form processes. Another case in the bond and form process is that we'll have unused material left in our box, and we can consider them as support, let's say, structures. And after the part is fabricated, you need to remove it out. And for some special machines, you may also make use of some ovens to remove them easily, but for simpler ones, you can take them out with your hands. Here's an example for bond and form process. Let me show it to you. Make it larger. Okay. Any questions, guys? This is the 3D printer. It's a bit huge. Again, they have a similar CAM software. The thing is that right now they are producing colored objects. You see this hammer has 2 different colors, and even it has patterns. And in the software, it's possible, since they are using sheet paper. Once you have colored sheet, so you can have at the end of this process a colorful object.
Paper-based 3D printing.
So this is how they do it. Let me go a little back. So these are sheet paper on top of each other, as you see, and they make use of a knife, sharp knife, and they put all these sheet paper on top of each other, and then the knife actually goes through this contour. And also, as you see, the remaining regions are divided into some squares, some box shapes, so that after the part is fabricated, they can easily be
Very
removed.
easy to use, but it doesn't run on toxic chemicals like some of our competitors.
Another paper now is cutting the contour.
M-Core 3D printers include a piece of software called Slicer. And what Slicer does is that it takes in the digital file and it slices the model digitally, each layer equivalent to the thickness of a slice of paper.
So can anyone tell me the output of their CAM software? So what is the software outputting? No.
Sheet metal, sheet profiles.
PDF file kind of, or just image files. Then what you are going to do, you will take all these images of the slice and simply print on your conventional printer, on 2D printer, inkjet printer.
If you're printing in color, you have two options. Either you get your file with your color information on it, or if you don't have that, you can use another piece of software by M-Core called Colors, which enables you to apply color to a regular STL or white file before sending it to Slicer. Once the color has been applied in Colors, you then import the model into Slicer and prepare your model on the screen before you send it to the actual 3D printer.
They are using a bit modified inkjet printer, but almost the same.
Printing in color is a two-stage process. So when you have your color model in Slicer, when you hit generate layers, not only does it work out the cut profile around the geometry, it also works out the color along that path. Then we hit print and we send that color information to the 2D printer that takes the M-Core ink and prints that color in duplex onto each.
So why do you think they have such markers around?
Konumunu sabitlemek için mi acaba?
Yeah, to align actually these papers on top of each other. Since they do not have any, I think, special equipment for that, by simply doing some image processing, they try to adjust the position of these papers.
We then take those sheets of paper and load them into a 3D printer for 3D printing.
So this is kind of their material supply.
The process that we have invented is called selective deposition lamination, or SDL. And as the name suggests, we selectively deposit the adhesive. So what that means is that on the very first layer, we apply adhesive, but in two different ways. On the waste material, we put down a very low density adhesive. And on the part itself, we put down a very high density adhesive. Then what happens is that a new sheet is pulled in from the paper tray. It's placed on top of the freshly applied adhesive. The whole plate is pressed against the heat plate, which makes sure we have a positive bond.
Yes, now they are pressing, and they have also deposited some adhesive on the paper. And with the help of this pressing, they make sure that the layers are joined properly.
The build plate comes down and it's ready for the next process. When the build plate returns to the build height, an adjustable puncture carbide blade cuts just one layer at a time, tracing out the object that we're trying to make. When the cutting sequence is complete, the machine immediately starts to apply the next layer of adhesive. A new layer is pulled in, pressed together, and cut, and the whole process is repeated over and over until all the layers are pulled into the machine. When all the layers are done, the part is finished and can be removed. The whole benefit of the SDL process becomes apparent when you actually try to remove the waste material from the finished object. Because we applied higher density.
So these are the cubes actually, and as we discussed, it's kind of a support structure.
Adhesive for the part and lower density adhesive on the waste. It means that the waste material comes off very easily. Also, to make it easier to remove the waste material is cut up into cubes, or as we call it, dicing, which means that the waste material can be removed very easily into nice little blocks. That means that you can get very intricate parts out of your model when it's finished. Unlike other technologies, M-Core 3D printed parts
So you can see some other examples.
So offers distinct advantages in for quality 3D printing. There is no more affordable.
So they are highly flexible, and we can print such colorful objects with the help of their technology. Any questions, guys, before we move on?
Hocam kullandıkları kağıt nasıl bir şey?
I think it's a bit thicker than our usual paper. A bit thicker. They are using some extra material, but they say that they are doing some kind of recycling. But obviously these regions, the support regions, are all kind of waste. So maybe you can print many parts at the same time, like we are doing in powder bed fusion processes. Instead of just printing a single part, they may have a couple of parts and print it in the same block. So now let's move on. We have a company called Lamination. They are using, instead of paper, using PVC plastic sheets, and they have similar other components, and they try to fabricate such parts with the help of laminated object manufacturing technology. Again, the fundamentals are the same as I said. The remaining part on the slices are divided into squares so that it will be easier to remove. This is their machine, the schematic of their machine. But instead of paper, they are using an PVC material. They are using a knife, not a laser, but the rest is the same. So for the bond and then form processes, we may make use of different materials, but obviously for metals it's quite difficult. There is some research going on, but we don't have a proper commercial system employing metals as the raw material. We can use ceramic sheets of ceramic material or composite materials like carbon fiber, glass. But the thing is that if you are using ceramics or other composite sheets, you need to do some further sintering or pressing operations. So what are the advantages of bond and then form processes? First of all, we have less shrinkage since we are properly bonding them first and then doing the cutting operation. We can assume that they are kind of single block. That's why we have less stress, less shrinkage, and we have less distortion between the layers. And if you are using paper, obviously the result is kind of a wood, a plywood, very similar. The mechanical properties are similar to plywood. And you can obtain larger products easily following the same scheme. You can do it in a rapid way, and you can make use of different materials like paper, different polymers, metals, ceramics, but these are metal and ceramics are quite difficult to use. And the materials are non-toxic usually. They are stable and you can easily handle them in your feedstock. And compared to the other manufacturing systems, the costs are usually low since most of them don't have any lasers. They are using simple XY plotter systems. The material is just paper or some simple polymers. So we can say that the overall system is have low cost compared to other systems. What are the limitations, the drawbacks? You need to have some proper coating of this, let's say, adhesive material, and you shouldn't have excessive layer on the previous layers. And the accuracy, especially in the Z, is quite difficult since you are putting these sheet materials on top of each other. You may have some bumps around, and that will actually decrease your accuracy in Z axis. Another problem is obviously this is actually the problem in most of the additive manufacturing processes. We will have inhomogeneous properties in different directions. So they will have anisotropic properties, and even you have another addition. If you do not distribute the glue properly on the layer, then that will result in another anisotropy, and you will not be able to control all these properties uniformly. And it's quite difficult to obtain actually small features, since we are doing kind of carving operation, like with the help of these knives and some lasers. Sometimes it's quite difficult to have such small features. Then now we have the second type of process called form and then bond process. As the name implies, in this type of processes, we will be first processing the layer on somewhere, and then after it is done, we will bring it and put it on the previous layers. And it's mostly useful for ceramic and metallic parts, metallic materials. We have a company called Offset Fabric System using this approach, and they have a special carrier which has adhesives, and they carry their sheets with the help of this one and then put it on to the previous layers. And they are using a special knife. Now I will show you a schematic. This is the carrier, and it has a kind of an adhesive on this side, and this is the raw material, sheet material. With the help of the knife, they are cutting through the contour, and after forming operation is completed, they turn it upside down and put it on the fabricated part. This is the object being fabricated, and now they are actually bringing this layer and trying to join it, trying to bond it to the rest of the part. But obviously the positioning here is quite important, and the advantage is that, as you see, even they have such an internal shape, internal feature here, they don't use any support structure. This is simply bonded to the previous layer. A nice advantage of formed and bond processes. So we can say that parts having internal features or any channels can easily be fabricated, which is actually not possible in the bond and then form approach. Another advantage is that you don't have any danger of cutting into the previous layer, since the part is formed in a separate region and then bonded to the previous ones. But in the case of bond and then form approaches, we are using a knife or a laser, and that knife may go into the previous layers and we may be damaging the previous layer. But it's not the case in formed and bond processes. And obviously, after the part is fabricated, we don't need to have any carving operations. Part is already finished. Even you have internal channels, you don't need to do extra carving operations. But we have some disadvantages. What are they? The first one is, if you especially have some overhanging features like this one here, you need to have some support structures. Let me try to draw it here. For instance, if you have this part quite a bit longer, like this one, then you may need to have a support structure underneath. But if it's not that long, you can handle it without using an extra support structure. So another disadvantage is about the placing of the new layer on the previous layers is quite important. The accuracy of this placement should be as high as possible, since otherwise, for instance, if you think about this internal feature, if you move it, let's say, some micrometers to the right, then you will have a kind of a bump here. And in the other layer, in the upcoming layer, this bump will be more effective. So the positioning is highly important, and you need to find some ways for proper placement of these sheet material. Any questions, guys?
Hocam bu proses ilk anlattığınız CBAM'le aynı mı?
Somehow similar, yes. We are forming it and then bonding to the previous layers.
Teşekkürler.
You're welcome. Now we have a bit special process called computer-aided manufacturing of laminated engineering materials. And we use it for ceramic and metal parts, but the thing is that they have a quite high amount of shrinkage. And with this approach, we can put different materials on top of each other. For instance, you may have a layer of ceramic and then a layer of metal. It's a nice property. And another advantage is that you can have internal features, like in the case of other form and then bond processes. So you can easily, it's a very difficult process. You can easily obtain functional parts and do some early testing. And it's especially useful for microfluidic structures since they have very little features and very complicated features inside. You can have it with the help of this CAM and LEM process. This is how they do it. They put it on top of each other, similar to the first process we have seen, like the impossible objects. They do lamination and then the binders are removed and they have the final part. And if you follow this approach, you can have various internal features. So that's why they use it especially for microfluidic applications. You see we have many channels here, water or other kind of fluid is moving through these channels and probably they are trying to eliminate some components inside. So it's a nice way, it's a nice approach to obtain such complicated shapes. This is another example for form and then bond process. It's called as subtle conception. It's very simple. I don't want to show you the video, but first let me show you this image. As you see, we have a large bear and it's divided into such layers. The thing is that they have some supporting, let's say, beams around, like this one here probably, and then they put all these layers into these beams and try to have such larger products. And obviously, you need to do some machining first. You need to obtain these layers by using CNC machinery and then put them on top of each other, glue them. But for better dimension accuracy, you need to have obviously some high quality CNC machining centers. If you just use a router, then your accuracy will be quite low. And most of the actual statues are, some of the artworks are done with the help of this conception or concept, which is called as subtle conception.